Hey there, Algebra 2 students. Welcome back to Miss McGuire's classroom. Of course, I'm Miss McGuire, and today's lesson is going to be focused on Unit 4, Lesson 4. Remember to put your first and last name, the period, and the date in the upper right-hand corner of your paper. Our topic today is solving higher degree polynomial functions and complex conjugates. So we're going to be talking about two things today. We're going to learn how to solve polynomial functions that have a degree higher than 2. We're also going to talk about these things called complex conjugates. So our lesson today is kind of jam-packed with a lot of information. Let's start diving right in. Our objective is I will solve higher degree polynomial functions that include complex solutions. I will also be able to factor using complex conjugates. Mastery will be demonstrated by scoring at least an 80% on our extra practice. So let's talk about a couple things here. The first thing I want to talk about is why the degree of a polynomial function is important. So when we had degree 2, like if we had like x squared minus 4 equals 0, how many roots or zeros or x-intercepts would this function have if we solved for them? This function would have 2 solutions. Well, I know that this function has 2 solutions because it's degree 2. So the degree of the function matches the number of solutions a function is going to have. So the degree of a function is the same number as the number of roots, also known as zeros, also known as x-intercepts, also known as solutions the function has. So the degree of the function is the same number of roots that the function has. All right. Some of our roots can be real, imaginary, and have what we call multiplicity. And I'm going to tell you what multiplicity means in just a second. So the degree of the function matches the number of solutions that the function has. Roots can be real, imaginary, and have multiplicity. And multiplicity is a new concept for today. So what a multiplicity of roots, and remember, roots is just another way of saying zeros, which is just another way of saying x-intercepts. So the multiplicity of those x-intercepts or zeros just means that that root can occur at the same point multiple times. The same point multiple times. So for example, if we have here we go, I'll do it right here. Let me show you what multiplicity looks like in an equation. So if you have x squared is equal to 0, this is a degree 2 term. So that means that because it's degree 2, that I'm going to have 2 roots, right? Which is something we just talked about. But when I solve this equation, so if I solve this equation, I have x squared equals 0. If I square root both sides, technically when I square root both sides, I'm going to get plus or minus the square root of 0. But the square root of 0 is just 0. And positive 0 and negative 0 are just 0. So it looks like I only have one solution, x equals 0. Well, what's happening though is that I have this one solution twice. Because I have degree 2, I need 2 roots. I need 2 solutions. So what I say is that x is equal to 0, multiplicity 2. So that means that x equals 0 twice. 0 is our only answer, but it's technically happening twice. And that multiplicity is going to come up in just some more examples we're going to do. So if you look at this equation, this is the graph of this equation, right? This equation is degree 2 because the highest exponent in the equation is 2. And I can see clearly that I have 2 x-intercepts. So I have 2 roots. I have 2 real roots here and here. And there's no multiplicity. If I look at this y equals x cubed minus 4x graph, I've got 1, 2, 3 roots, which matches my degree 3. So I've got 3 real roots, and again, no multiplicity. None of these roots happen more than once because I have 1, 2, 3 roots. Well, when I look at this x to the 4th, y equals x to the 4th minus 3x cubed minus x squared plus 2x. Again, I have 1, 2, 3, 4 roots, which matches my degree 4. All right, but look at this equation and its graph. Y equals x to the 4th plus 2x cubed. It's still degree 4, which means I have 4 roots. But on my graph, I only have 2 roots showing. There's only 2 roots showing. So that means that these 2 roots could have multiplicity. They could be occurring more than once, or I have 2 imaginary roots as well. And so what we're going to learn to do today is we're actually going to learn how to solve these functions and find out, okay, are all 4 of those roots real? Are some imaginary? Are some happening multiple times, more than once? And that's what we're going to be exploring. So as you can see on this graph, y equals x squared, we already solved this up above here. And we figured out, well, the only solution you can get is x equals 0. So the only solution is x equals 0, which means that this graph is happening at, this graph has an x-intercept at x equals 0 twice. So this 0 has multiplicity of 2. Hopefully I just spelled that word right. All right. Then y equals x squared plus 2. Well, this graph doesn't even cross the x-axis. So that means that both of my zeros, this is degree 2, I should have 2 zeros, are imaginary. I have 2 imaginary roots. And there's no multiplicity because the 2 roots are occurring on the imaginary number line. All right, so let's jump into some algebraic examples. So y is equal to x cubed minus 4x, which is actually this equation here. We're going to mathematically find these x-intercepts, and then we'll see if our answers match our graph. So y is equal to x cubed minus 4x. So the first thing we're going to look for is this equation factorable? Well, if you look at x cubed minus 4x, there's a GCF here. These guys have a GCF of x. So what if I factor out that GCF? So I'm going to have x times. If I factor out an x from x cubed, I'll be left with x squared. If I factor out a 4x, an x from 4x, I'm going to be left with a negative 4. And then I notice that this is a difference of squares. And remember, to factor a difference of squares, so we have x squared. Sorry, let me do this. Remember, when we factor a difference of squares like a squared minus b squared, we do a minus b times a plus b. So this is then going to factor to x minus 2 times x plus 2. And you can multiply that back out and just make sure and double check that it does simplify to our original function. All right, so now remember when we solve by factoring, so the first thing we do is we factor everything. Then, oh, I forgot the most important step. We plug in 0 for y. Should have done that at the beginning. Then we take each factor and set them equal to 0. So we're going to set x equal to 0, x minus 2 equal to 0, and x plus 2 equal to 0. And then we solve for x. So I'm going to add 2 to both sides. I'm going to subtract 2 to both sides. And I have my 3 answers, x equals 0, 2, and negative 2. So I get x equals 0, 2, and negative 2. And I found all 3 of my x-intercepts. So I noticed that I started with a degree 3 polynomial, which means I should have a total of 3 zeros, 3 solutions. And I was able to find them all algebraically, 0, 2, and negative 2. And let's see if that matches our graph. Well, I see an x-intercept at x equals 0, x equals 2, and x equals negative 2. So we must have done something right. And then, you know, normally I would make you guys write them as x-intercepts, where you would tell me 0, 0, 2, 0, and negative 2, 0. And then your zeros are x equals 0, 2, and negative 2. All right, why don't you guys try one on your own? So the first thing you're going to want to do is, of course, set y equal to 0. Then you're going to want to notice, well, what degree is this? This is degree 3. So because it's degree 3, that means you should have 3 zeros, or 3 x-intercepts, or 3 roots, whatever words you want to use. You might notice that these all have a GCF, and then you're going to want to see if you can factor it even more after that. So why don't you go ahead and try to factor this thing completely, and then press pause, and then press play when you're ready to check your factors, and then we'll solve it from there. So go ahead and factor this thing completely. Give it a shot. You know what, though? I actually just realized that the GCF is actually 3x. 3 goes into 3, 15, and 8. So instead of just factoring out an x, you can also factor out a 3. All right, now see if you can factor this thing completely. Go for it. So after I factored it completely, I got 0 equals 3x times x plus 3 times x plus 2, because I recognized that I could factor x squared plus 5x plus 6. And if you need help remembering how to factor, you can always hit the ask for help button and I'll walk you through it in your breakout rooms. But when you have x squared plus 5x plus 6, I'm going to go ahead and do this off to the side. Remember, you take a times c, which is 1 times 6, which is just 6. Then you take the factors of 6 that add or subtract to get 5. But we want a positive 5 and a positive 6. So I'm going to use positive 2 and 3. So x squared plus 2x plus 3x plus 6. Then you put parentheses around the first 2 terms, the last 2 terms, make sure there's a plus sign in between. You factor out what each pair has in common. Then when the parentheses match, then you know you have x plus 2 as a factor and then x plus 3 as a factor, which matches what I have up here. All right, now you're ready to set each factor equal to 0 and solve for x. So go ahead and do that. Press pause and then press play when you're ready to check your answers. Go for it. So as you can see, I found 3 real solutions. I got 0, 0, negative 3, 0, and negative 2, 0 for all 3 x-intercepts that this function will have. So for those examples, we ended up with all real solutions, which is great. But there's going to be times where some of our x-intercepts are imaginary, some of them are real, some of them have multiplicity, all that good stuff. So let's keep going. Part C, y is equal to 10 to the 4th minus 4x cubed plus 10x squared. So as you can see, we have degree 4. So we're looking for 4 solutions total, or 4 x-intercepts, 4 zeros, 4 roots. So the first thing I'm going to do is I'm going to plug 0 in for y. Then I'm looking for the GCF. And I noticed that 2 goes into 10, 4, and 10. And x squared goes into all three of these. So I'm going to factor out a 2x squared. So 2x squared times 5x squared would get me 10x to the fourth. 2x squared times negative 2x would get me negative 4x cubed. And then 2x squared times 5 will get me 10x squared. All right. So then I need to see, is 5x squared minus 2x plus 5 factorable even further? To do that, I'm going to take 5 times 5, a times c, which is 25. And then are there factors of 25 that add or subtract to get me negative 2? And no. So this isn't factorable any further. So that means that I'm ready to set each factor equal to 0. So I'm going to have 2x squared equals 0. 5x squared minus 2x plus 5 equals 0. So then to solve 2x squared equals 0, I'm going to divide both sides by 2, and I get x squared equals 0. Then to cancel a square, I'm going to square root both sides. When I square root both sides, I get a positive and a negative answer. But positive 0 and negative 0 are the same thing. So then x equals 0. But because it was x squared equals 0, that means that this has a multiplicity. And so I'm going to say multiplicity, and we can shorten that by just writing multiplicity 2. So x equals 0, multiplicity 2. And I know that because I started with a degree 2, so this answer happens twice. All right, let's do the next one. Well, since this wasn't factorable, I'm going to plug this. This is a degree 2. I'm looking for 2 solutions here. I'm going to plug this into the quadratic formula. So x is equal to the negative of b plus or minus the square root of b squared minus 4 times a times c all over 2a. So I'm going to get the negative of b, which is, oops, just kidding. Why didn't I just fill this in? Negative 2. I'm going to fill in a and c. So the negative of negative 2 is 4. Negative 2 squared is 4, minus 5 times 5 is 25, times 4 is 100, all over 10. So x is equal to 4 plus or minus the square root of negative 96. Now this is why this wasn't factorable, because we've got a negative under a radical, which means we're going to have imaginary solutions here because we're going to have to use I. All right, so x is equal to 4 plus or minus the square root. I'm going to replace this with negative 1 times 96 all over 10. How can I break down 96? Let's see, 96 divided by 4 is 24. So 4 times 24. Then I'm going to break down 4 as 2 times 2, and 24 is 4 times 6. I'm going to break down 4 as 2 times 2, and 6 as 2 times 3. And I just did that all in the same step so I could save some space here. So 4 plus or minus, I'm going to replace that negative 1 with I squared, which is just I times I. I'm going to bring out an I, a 2, and a 2. So 2 times 2 is 4. So I'm going to bring out 4i, and I'm left with 2 times 3, which is 6 under the radical. And then we have 10. So now because 4 over 10 and 4i over 10, 4i root 6 over 10 can reduce, I can simplify this to be x is equal to, all of these are divisible by 2, so I'm going to say 2 plus or minus 2i root 6 over 5. Whew, wow. And notice how many imaginary solutions do I have here? I actually have 2. I have 2 plus 2i root 6, and I have 2 minus 2i root 6 over 5. So we found our other 2 answers. We have x equals 0, multiplicity 2, and then we have these 2 imaginary solutions as well. So my final answer here is my zeros are x equals 0, multiplicity 2, comma, 2 plus 2i root 6 over 5, and 2 minus 2i root 6 over 5. And there we go. We found our 4 zeros, our 4 solutions. Now, if you wanted to write these as x-intercepts, we can't graph the imaginary solutions, so you don't have to write the imaginary solutions as x-intercepts. You would just tell me the real one, which is 0, 0, because that's the only one we would care to graph. We're not going to graph the imaginary ones on the real number. All right. And then, of course, I would have accepted these answers too if you had still written them together. These two, if you had written them as 2 plus or minus 2i root 6 over 5, that would have been fine too. All right, why don't you all try one on your own? So remember, the first thing you're going to do, notice the degree. How many roots are you trying to find here based on the degree? Then plug in 0 for y and then do as much factoring as you can. And then if you have to use a quadratic formula for some, just go for it. Give it a try on your own. Press pause and then press play when you're ready to check your work. I believe in you. You got this. So normally I have it all worked out and then I talk about it, but for this problem, I'm going to work through it and explain what I'm doing as I go, and then you need to compare it to what you did. So the first thing I notice is, of course, it's degree 5. So I'm looking for 5 roots. You might call them x-intercepts. You might call them zeros. We're talking about the same thing. All right. So I'm looking for 5 roots. The next thing I'm going to do is I'm going to plug in 0 for y. Then I'm going to start factoring as much as I can. I'm looking for a GCF. So I notice that 4 goes into 4, 24, and 48. I notice that all of these have at least 3 x's, so I'm going to factor out an x cubed as well. Let's see, 4x cubed times x squared would get me x to the 5th. 4x cubed times negative 6x would get me x to the 4th, negative 24x to the 4th. And then 4x cubed times 12 would get me 48x cubed. So the next thing we want to look for is this factorable further? Let's see, factors of 12, the add or subtract to get a 6. 1 times 12, 2 times 6, 3 times 4. None of these would add or subtract to get 6 in the middle, so this isn't factorable. All right, which means we can go ahead and just split this thing. We're going to put each factor, so this factor, 4x cubed, equal to 0, and solve for x. We're going to put this factor, x squared minus 6x plus 12 equal to 0, and solve for x. 4x cubed equals 0, divide by 4 on both sides, x cubed equals 0. And then I guess I haven't taught you guys how to deal with x cubed equals 0 yet, but you know how we use a square root to cancel a square? You can do a similar thing with cubed roots and just take the cubed root and then guess what the cubed root of 0 is? 0. So x equals 0. Easy enough to deal with. But how many times does that occur? X cubed had equaled 0, which means that the 0 is actually occurring with a multiplicity of 3. Now we need to deal with this. It's not factorable, so I'm going to plug it into the quadratic equation formula. Sorry, x is equal to the negative of b plus or minus the square root of b squared minus 4 times a times c all over 2a. Hopefully you plugged it in correctly. Let's see, the negative of negative 6 squared, negative 4 times I just like spaced out for a second, sorry. A is 1, C is 12. There we go. So we're gonna have positive 6 plus or minus the square root of 36 minus 48 all over 2. We're going to have 6 plus or minus the square root of negative 12 over 2. So negative 12 is negative 1 times 12. And to save room, I'm going to do all of this in the same step. So bear with me. I'm going to replace negative 1 with I squared. I'm going to replace 12 with 4 times 3. I'm going to replace 4 with 2 times 2. I squared can get broken down to I times I. So I've got a group of 2 i's, a group of 2 2's. I can actually bring out 2i root 3 over 2. Now, because 6 over 2 will reduce and 2i root 3 over 2 will reduce, both of them do, I can go ahead and reduce that. 6 divided by 2 is 3. 2i divided by 2 is just I root 3. And check it out. We found our other 2 solutions. So I've got 2 of my zeros here and 3 of my zeros here. So I found all 5 of my roots. So my final answer is, you're going to say your zeros are x equals 0, multiplicity 3, and then 3 plus or minus I root 3. And of course, you could write it as x equals 0, multiplicity 3, and then 3 plus I root 3, 3 minus I root 3. I'll accept either of those answers. Then the only x-intercept we would worry about, since these guys are imaginary, we're not going to graph them. We're not going to actually use those x-intercepts on the real number plane. So the only x-intercept you would have to worry about is the x equals 0. So 0, 0 would be that point. All right. Hopefully your answer matched mine. Now we're going to talk about complex conjugates. So complex conjugates is just like a fancy term for saying that a complex number has a pair and that they come in pairs. So complex conjugates look like, if you have a complex number like a plus bi, its complex conjugate is a minus bi. So anytime you have a complex number, there is always a pair with the opposite sign. And that should make kind of sense to you, because in all of our problems where we had I, right, our imaginary number, there's a pair of numbers here. We have 2 plus 2i of root 6 over 5. And then what is its complex pair? Its conjugate would be 2 minus 2i root 6 over 5. And we got those 2 answers by using the quadratic formula. But if we didn't have the quadratic formula and I just said, hey, here's one of our solutions, what's the other one? You would be able to tell me that it would be 2 minus, because we know when we take the square roots of things, we get plus or minus. We get 2 answers, 2 solutions. So that's where complex conjugates kind of come from. If you have a plus bi, you know that you have a minus bi. So for example, let's say that I had 2 plus 4i as one of my solutions. What would its conjugate be? What would its pair be? Its pair would be 2 minus 4i. Okay, what if I had 1 minus 3i? What would its pair be? 1 plus 3i. Okay, what if I had just 4i? What would its complex conjugate be? Negative 4i. What if I had negative I? Its pair would be positive I. So complex numbers travel in pairs. There's always 2. If you have one, you know you have the other. And it always has the opposite sign right before the complex part. So what we can do is we can use those to factor things. Well, let's try something out real quick. Let's take 2 plus 4i and just do this off to the side on your paper. 2 plus 4i times 2 minus 4i. What do I get when I multiply a complex number by its conjugate? We'll check this out. 2 times 2 is 4. 2 times negative 4i is negative 8i. 4i times 2 is positive 8i. 4i times negative 4i is negative 16i squared. Well, wait a second. What's negative 8i plus 8i? Don't those cancel? It's 0, right? So this would be 4 like minus 0, which is just 4. And then negative 16i squared, well, isn't I squared equal to negative 1? So I just replace I squared with negative 1, and I get negative 16 times negative 1, which is 4 plus 16, which is 20. Check it out. If I take a complex number and I multiply it by its conjugate, I'm left with a real number. If I take the imaginary number 2 plus 4i and I multiply it by its imaginary complex conjugate, 2 minus 4i, I'm left with a real number. Let's do that one more time. Let's try 2 minus 3i times its conjugate, 2 plus 3i. Multiply that one for me real quick and tell me what you get. Press pause and then press play when you're ready to check your work. So I ended up with 13. I got 4 plus 6i minus 9i squared, which is 4 minus 9 times negative 1. 4 plus 9 is 13. So let's use that information to help us do some factoring. So we learned how to factor x squared minus 81, a difference of squares, right? Where we took x minus 9 times x plus 9, because when we multiply that out, we end up with middle terms that cancel out. So now we're going to learn how to use the imaginary number I to help us factor x squared plus 81. So I'm thinking to myself, well, I know that x times x will get me x squared. And I know that 9 times 9 will get me 81. And if I take positive 9 times negative 9, some things will like cancel out for me, those middle terms. But if I multiply this out, I'm going to get x times x is x squared. X times negative 9 is negative 9x. 9 times x is positive 9x. And positive 9 times negative 9 is negative 81. Well, what's handy here is that these middle terms cancel, but I'm left with a negative 81. How could I turn negative 81 into positive 81? Well, what if I multiply it by negative 1? And then I think to myself, well, wait, what do I know is the same thing as negative 1? Isn't I squared equal to negative 1? So what if I replace this negative 1 with I squared? And then how would I get negative 81i squared by multiplying 9 and negative 9? Would I get it by multiplying 9i times negative 9i? I don't know. Let's see what happens. So x times x is still, and I'm just, distributing all of these things. X times x is x squared. Sorry. X times negative 9i is negative 9ix. Positive 9i times x is positive 9ix. Positive 9i times negative 9i would be negative 81i squared. We'll check out these like terms. Negative 9ix plus 9ix cancels. So I'm left with x squared minus 81i squared. Well, what do I know that I can replace I squared with? Make sure you put it in parentheses, a negative 1. Well, what's negative 81 times negative 1? Positive 81. Check it out, it worked. So I know that x plus 9i times x minus 9i factors to get me x squared plus 81. And x plus 9i and x minus 9i are complex conjugates. They're the same imaginary number, but with a positive and a negative. So let's try x squared plus 9. X squared plus 9. So why don't you try this one on your own? Set up your parentheses. What times what will get you x squared? What times what will get you 9? And then how do we use I to help us end up with a positive 9 when we multiply? Press pause and then press play when you're ready to check your work. So I tried x minus 3i times x plus 3i. Now let's multiply it out just to check and make sure that we are right. So x minus 3i times x plus 3i. I'm going to distribute the x to the x and the 3i, and I get x squared plus 3ix. Negative 3i times x is negative 3ix, and negative 3i times positive 3i, negative 9i squared. I realize my middle terms cancel, and then x squared minus 9i squared. I squared can be replaced with negative 1. I put it in parentheses and multiply it by the negative 9, and I get x squared plus 9. So it worked. Go us. Now, one thing I'd like to point out before we do the next problem is, what was the square root of 81? The square root of 81 is 9, and 9 got put here and here. What was the square root of 9? The square root of 9 is 3, and 3 got put here and here. So now I'm going to do x squared plus 8. Now the tricky thing is, though, is that 8 doesn't have a square root. It can simplify, but we'll do that later. The square root of 8 isn't like an integer. It's not a perfect square. So what we're going to do is the same concept when we factor x squared plus 8. We're going to have x times x to get the x squared. And then we're going to have the square root of 8 times the square root of 8 to get a positive 8 when we multiply it. And we're going to do a positive and a negative. And then we're going to want to make sure that we include I. So we're going to put I in front of the radical. So let's multiply this out and make sure that it works. So what's x times x? X squared. What's x times negative I root 8? Negative I root 8x. I root 8 times x is positive I root 8x. And then I root 8 times negative I root 8 is negative I squared times the square root of 8 times the square root of 8. All right. So these terms are the same with opposite signs, so they cancel. I'm left with x squared minus I squared gets replaced with negative 1 times the square root of 8 times the square root of 8 is the same thing as 8 times 8 under 1 radical. Erase this so it's out of the way. So then I've got a pair of 2 8s that I'm going to bring out in front of the radical. So x squared, a negative times a negative is a positive, and then I have an 8. And nothing's left under the radical. So I have x squared plus 8 left. So it worked. And notice these are complex conjugates. X plus I root 8 and x minus I root 8 are the same thing, just with opposite signs in the middle. Now, why don't you try x squared plus 3 on your own? So remember, you're going to do something times something to get x squared, and then the square root of 3 times the square root of 3 to get 3. Go ahead and give it a shot, press pause, and then press play when you're ready to check your work. So I got x plus I root 3 times x minus I root 3. Because I know that I want opposite signs, so my middle term will cancel when I simplify. I know that I want the I, so that way I get I times I, which is negative 1. So I can change it back to a positive at the end. And then, of course, I can multiply it out to check and make sure that I'm right. So let's do that. X times x is x squared. X times negative I root 3 is negative I root 3x. I root 3 times x is I root 3x. I root 3 times negative I root 3 would be negative I times I is I squared. And then root 3 times root 3 is root 3 times 3. So we get I squared. Our middle terms cancel. Negative times negative 1, root 3 times 3. I'm going to bring that 3 out in front of the radical. Negative times negative 1 is positive, and we get positive 3, which matches our problem that we started with. So here we go, we did it. All right, so today you're actually going to skip the extra practice. I know I mentioned it in the objective. Instead of the extra practice, though, you're going to jump straight to your homework, and your homework will be found on Schoology instead of Math Excel. So your homework is on Schoology. You're going to complete all of the problems, then you're going to check the answer key attached to the assignment, and you're going to put your grade at the top before you turn it in. So go ahead and get started on your homework, and I'll see you back in class. I hope you have a good day. And of course, hit that ask for help button if you need any extra